because a derivative describes a rate, it doesn't just describe things like velocity. Velocity is specific to physics, but rates can be applied to lots of other things. It doesn't have to be physics. It could be biology, it could be economics, it could be geology. The derivative can describe the rate of growth of anything. Okay, so we're going to use derivatives to describe anything that changes. So we're going to do growth rate. That could be of a population. It could be of a virus. It could be of, a beanstalk. I mean, anything you could use it to describe growth rate. We're going to use it to describe economic growth. And we're going to use it for any other rate of change. So just some examples to kind of get you thinking of things that change. All right, if T is the tide depth, so this is a geological thing. Okay, so if the function T, capital T, describes the depth of the tide, tide goes in, tide goes out, tide goes in, tide goes out. This is a physical situation in our physical Earth. Then D capital T, and then D little t is the changing rate of the tide. Okay, so just keep thinking, all right, derivative is talking about how that thing is changing because it doesn't stay the same. If M is the phase of the moon, then M prime of T is the changing rate of the moon's phases. Everything is just a rate. Depending on the time that's gone by. Okay, usually that happens every 28, 29 days. Okay, the changing of the moon. Okay, if V is the volume of a lake, that volume changes depending on how much snow there was or how much drought we're in. Okay. Then dV dt is the changing rate of the volume over time. With respect to time is how we read that. When you say with respect to something, it means that that thing changed first, which impacted the thing I'm talking about. In other words, the time changes first. I can't control time. Time is going to change with or without me. Because time changes, then the volume of the lake changes. The time happens first. For the moon, I did T also for the time. We can't control the time of the days that are going by. The days change, therefore the moon phase changes. One depends on the other. Time is always independent. It's an independent variable. Okay, the depth of the tide depends on the time. The phase of the moon depends on the time. The volume of the lake depends on the time, depends on the season that you're in. Okay, so when we say with respect to, it's what it's dependent on. All right, those are all some physical, geological examples. Let me give you an economics example. Okay, if B is the value of a bond, then B prime of T is the changing value, the changing rate of the bond's value. In economics, there's a special word that they use. They don't use the word derivative, but it means the same thing. In economics, they use the phrase marginal, which implies the first derivative. A margin is a very small amount of time. It's the change over a very, microscopic, it's not a change over a large amount of time, it's the change in a small thing. So if they talk about the marginal revenue, marginal profit, marginal cost, marginal growth, it always is implying that you get to take the first derivative, because that's what marginal would refer to. So I want to do an actual example of that with you. Wrong page. Okay, it's different than average. So those two things. Average is over a period of time. One uses calculus, one doesn't. Marginal is the first derivative, that uses calculus. Average doesn't, and it's more like f of b, or it is exactly like f of a over b minus a. It's the slope, it's the average, whereas the first derivative would just be f prime. What they're useful in economics is that marginal looks to the future, whereas average looks to the past. That's a good distinction to think about the two of these things. Okay, marginal is looking to the future, what's going to happen in a short amount of time. Average looks to the past, what already happened in the past. Okay, with average, you're taking actual data of something that actually happened. For marginal, you're taking an educated guess about what will happen in the future based on the derivative, which takes the slope of where you're at and sends you off in that continued direction. Okay, so here's an example. All right, you decide, you win the greatest British baking show, and you decide you're going to open your own bakery, okay? You're like the star baker now. All right, but you've got some costs incurred in that. So your cost function is c of x, and it's going to be a cubic function. The thing we know about cubics is they start going up for a while, but then what happens to the cubics? All cubic shapes. They start going up, then what happens to them? They'll start going back down, and then eventually what will happen to a cubic? You got to go back up. So if you're in business and your model is a cubic and you're in the down part, you just look, I just got to hang on, I just got to wait, because hopefully eventually this is going to turn around, because it's going to be a cubic. All right, heaven forbid you actually be on a parabola where you go up for a while and then you go down and there ain't no recovering from that, and your business is just going to go down all the way. Okay, so you're hoping that your business model is going to be a cubic model. Okay, so question A. Okay, you want to look back and find out what was your average cost. You've made 15 wedding cakes. Okay, that's what you were specializing in, cakes. All right, find the average cost for those 15. Okay, so this looks to the past and it doesn't use calculus at all. It'll be c of 15 minus c of 0 over 15 minus 0. Okay, it does not require calculus. So this, I worked it out. It's 2350 minus 100 over 15. And that works out to be $150. And that is your average cost per cake. Well, why does a cake cost that much? Well, because you had to go out and buy supplies, and then it took you time to make it. Hey, you could spend all day decorating some of these fancy cakes. So the cake is going to cost that much. Now, this is not what you're charging. You got to decide on your price later, but this is your cost. Okay, now we want to find the marginal cost. At x is 15. So now we're going to look to the future. So we're going to find c prime. C prime, based on our cost, is 3x to the second minus 12x plus 15. And I'm going to plug 15 into that, and I worked it out already, and it came out to be 510. That's the cost per cake. That's your future cost. Eek. That's not good. Your future cost shouldn't be more. Why? Well, maybe you're having to pay overtime. Okay, or maybe there was a scarcity, you've used up all the eggs or all the flour, and now there's a scarcity of commodities and you've got to pay more for your ingredients. Who knows? Okay, but now the cost is higher. What that is implying is that the 16th cake, if you would choose to make it, would cost you $510. Okay, it's not talking about the 15 cakes. The 15 cakes are done. The implication is that's what it's going to be for the next one that you're going to do. So now you as a business owner have to decide what you're going to do. Okay, so maybe you're going to be looking, well, if the average cost would go down, then you're like, yeah, no brainer, I'm going to make more because my cost is going down, I'm getting more efficient. But if your costs are going up in the future, then you need to change your business model and figure out, or you're going to have to increase your price to cover the increased cost. Okay, you can do this with n-deriv on your calculator as well. So this last thing, if you could get out your calculator, because some of your function models are going to be this was a really easy model. It's just a very simple cubic. Some of your business models are going to be a lot more complex. So just a reminder. Okay, let me give you an equation to put in. 25 over the quantity, so make sure you use parentheses, of 1 plus 10 times 2 to the 7 minus 0.3x. So that should be your power, and then close the parentheses off. Okay, see what I did? 1 plus 10. Okay, this is a profit model. It's a profit model. Now we want to look at the marginal profit. So use n-deriv. That's math 8. I think I showed you this before. Math 8, which says find the derivative of that really complex equation for me that I don't know how to find the derivative of, but the calculator can. d dx. y1 is going to go right there. And then set that to just be x again so that it covers, if you put a number there, then it'll just give you a one dot derivative at the number. We want to know the derivative everywhere. Oh, under your vars. Okay, I can back up to there. Okay, vars, it's the y vars column menu, and we're working with functions. We pick the first one. And let's take a look at this graph. Turn off your y1, unhighlight it. You'll get, if you leave them both on, you'll get two graphs that cross. I would say just turn it off. And then let's set our window to go about 0 to 10 would be fine. And then your y min and your max can be fairly small. While you're working on that, I'm just going to check something a second. Okay, yeah. Let's go out, and we're gonna have to go a little farther. Okay, it takes the calculator a little while to graph it, but if we are looking for margin and we want the max, while you're waiting, okay, I set mine to 0 to 100 as my window. We want the maximum not to be the peak. That's not where the maximum is, not when you're looking at marginal. Where is the maximum when you're looking at marginal? When it crosses from? Okay, it crosses the x-axis. In what direction? From positive crossing to negative. That's where you're going to find your marginal. It's not, the maximum is not the peak. Not when you're looking at the derivative. When you're looking at the derivative, the maximum is where it crosses, if it crosses. If it doesn't cross, then there is no maximum. If it does cross, you do have a maximum. Alright, I'll see you Thursday.